Okay, let's dive right into this explainer. Hot aisle versus cold aisle containment. What if I told you that the secret to keeping the global internet running smoothly isn't just about faster microchips or better software? Actually, it comes down to managing, well, thin air. Today, we're going to discover how simply controlling airflow can dramatically reduce energy costs in a data center, literally transforming uncontrolled chaos into a highly managed system of efficiency.
What if rearranging racks saved millions? It sounds almost too simple to be true, right? But in the world of modern data centers, where energy usage is just off the charts, even the smallest inefficiencies inside a data hall can lead to major energy waste. Or honestly, worse, massive equipment failure. So we're going to look at one of the most absolutely crucial efficiency strategies in the industry today, breaking down exactly how facilities organize their physical space to survive the heavy loads of our digital world. Section 1. The data center heat problem. To really appreciate the solution, we first have to understand the core threat to our infrastructure, and that threat is simply heat.
Let's look at how this builds at the micro level. Step 1, every single server pulls cold air in the front. Step 2, it cools the internal components. And Step 3, it exhausts hot air out the back. Think of each server as a mini wind tunnel desperately trying to survive its own rising temperatures. It pulls that cold air in through its front intakes, uses it to cool its vital internal pieces, and then violently blasts the hot air out the back. Now multiply that by thousands of servers. You have a room-baking amount of thermal energy being generated every single second. So here are the consequences of mixed air. Higher energy consumption, reduced cooling efficiency, dangerous hotspots that actually damage equipment, and increased strain on cooling units. The crucial point here is what happens if that hot exhaust air casually mixes with the incoming cold air. It triggers a catastrophic domino effect. The cooling system suddenly has to work so much harder to maintain safe temperatures. This mixing directly leads to all those nasty consequences we just mentioned. It puts an incredible strain on the whole operation. The goal, then, is incredibly simple in theory. Separate the hot air from the cold air as much as humanly possible. Moving right along to Section 2, baseline airflow layouts. To fight this battle against mixed air, facilities had to start getting organized. We have a cold aisle layout where the fronts of racks face each other, versus a hot aisle layout where the backs of the racks face each other. The most common approach early on was to arrange server racks into these specific rows. In a cold aisle layout, cold air is blasted right into this central corridor, usually up through perforated tiles in a raised floor. The servers happily pull this cold air in. Or, alternatively, you can flip them to create a hot aisle layout. This forms a dedicated corridor where all that hot exhaust is concentrated and pointed back toward the cooling system. But there is a huge flaw here. Air still mixes above and around the racks. These baseline layouts definitely improve airflow compared to just a random room of servers, but as well organized as it looks on a floor plan, it has a fatal flaw, because air is fluid. Without physical boundaries, hot and cold air simply travel right over the tops of the racks and around the sides to mix anyway. You're still losing efficiency because the separation just isn't absolute. Section 3, the containment solution. To actually solve this heat problem and stop this wasteful mixing once and for all, we need physical boundaries. Enter the ultimate fix, containment. This means taking layouts to the next level by physically enclosing either the hot or cold aisle using ceiling panels, end-of-row doors, and airflow barriers to completely prevent air mixing. We are literally building walls around the air. By turning an open space into an aggressively managed, sealed system, we actually achieve our goal. We stop the hot and cold air from mixing entirely. There are two main strategies in this architectural showdown, starting with Section 4, cold aisle containment. The goal here is simple: trap cold air directly in front of the racks. In this configuration, it's exactly what it sounds like. The cold aisle itself is physically enclosed. By doing this, we ensure that the servers always, without fail, receive consistent, low-temperature air for their intakes. Meanwhile, all that hot exhaust air, it's just allowed to flow freely throughout the rest of the larger data hall. So let's look at the pros and cons. Pros: simpler retrofits, consistent inlet temperatures, and a lower upfront cost. But the cons: the overall room becomes warmer, there's lower efficiency at high densities, and the cooling system may still overwork. It's a fascinating trade-off.
You get that massive benefit of a lower upfront cost and easier installation in existing buildings, but because you are only trapping the cold air, the rest of the room gets incredibly warm, like walking into a sauna warm. And at higher equipment densities, this method loses its edge, meaning your cooling system might actually still be working way harder than it needs to. On the exact opposite side of the spectrum, we have Section 5, hot aisle containment, which flips the script entirely. The goal this time? Capture, isolate, and direct hot air back to the cooling system. Instead of trapping the cold, we are literally caging the heat. We isolate that hot exhaust right as it leaves the servers and funnel it straight back to the cooling units. Because the heat is locked away inside these enclosed corridors, the rest of the open data hall remains perfectly, refreshingly cool. The pros and cons shift dramatically here. Pros: higher energy efficiency, better high-density performance, and improved cooling operation. Cons: complex design and installation, fire suppression coordination is absolutely required, and a higher upfront cost. By managing that return air more effectively, you get incredible performance for modern, high-density setups. But you really have to earn it. You've got higher initial costs, and crucially, you have to carefully coordinate these big physical structures with the building's fire suppression systems, which is a whole other puzzle to solve. Section 6, the modern high-density winner. With all those pros and cons on the table, let's see which strategy modern engineering actually prefers. Let's compare them side by side. Primary focus: protecting equipment versus improving cooling efficiency. Upfront cost: lower versus higher. Ambient room: warmer versus cooler. High-density use: lower efficiency versus superior performance. This brilliantly illustrates the fundamental philosophical difference here. Cold aisle focuses on protecting the gear. Hot aisle focuses on optimizing the cooling system's return air. One gives you a warmer room and lower upfront costs, and the other gives you a cool room but demands a serious initial investment. The winner, hot aisle containment, is generally preferred for modern high-density data centers. Because modern facilities run incredibly dense, high-powered servers that generate just immense thermal loads, the hot aisle approach really wins out. Despite the complex installation, it offers far better control of those return air temperatures, unlocking the superior system performance that is absolutely mandatory for heavy, modern internet traffic. The macro impact? It dramatically reduces energy consumption, lowers operating costs, increases equipment lifespan, and ensures overall data center reliability. This is exactly why this matters to you, whether you're building data centers or just streaming movies on them. These massive physical infrastructure choices, literally choosing to build walls around hot air, are the hidden mechanics saving absolute fortunes in operating costs. It keeps the global internet reliable. If managing thin air saves massive facilities millions of dollars, what other invisible efficiencies are powering our digital world? It's just so fascinating that the backbone of our digital, wireless, cloud-based lives is so deeply dependent on heavy physical engineering and basic thermodynamics. I hope this explainer sparked your curiosity about the physical reality required to keep our digital clouds floating smoothly. Because, if managing something as totally invisible as airflow can save millions and prevent global outages, it really makes you wonder, what other invisible efficiencies are quietly powering our digital world right this very second?